this lecture, we're going to go over the matrix concepts. So we're going to look at matrices calculations. We're going to look at scalar, adding, subtracting, and multiplying. We're also going to do transposing matrices and doing a matrix inversion. We'll also go over an example. All right, first things first. A matrices is basically made up of rows and columns, and the reason that we use these is to solve, sometimes we use them in algebra to solve for unknowns. We use them for coordinate transformations, scaling, rotation, translation. We also use the matrix in least squared adjustments and photogrammetry. Least squared adjustments will be further in this semester. So, and a matrix, like I said, is just basically a rectangular array of rows and columns. And the way that it's written, you'll have a row and then the column is the number. So if you take a look at this matrices, we've got, you'll see, I'm going to go over some of the nomenclature of how things are written. This is a 3 by 3 square, so that means it has 3 rows, 3 columns. Now in this, you have a matrices, in your math books, it might be a letter with a bar over the top of it. So the rows are going horizontally and the columns will be vertically. Now in this lecture, we're going to say M is equal to the number of rows and N is equal to the number of columns. So we write 3 rows, 3 columns. Now in here, whenever you have a square matrices, it could be a 4 by 4, a 2 by 2, 5 by 5. That's what it means by square. Both the number of rows and columns are the same. When you have a diagonal, you have a major going from the top corner down to the bottom corner is going to be your major diagonal, and then you have a minor diagonal that goes from the bottom to the top corner in your square matrices. Okay. Again, just in summary, the matrices has a matrix M, or an M with a bar over top. It has M times N size. So you can also see if it's you'll see it as a multiplier or a comma written in some ways. When M and M are the same, then you have a square matrix. The 2 vertical lines, this line here and this line there, it basically denotes that this is a matrices. You'll see it in the books, okay? Sometimes not. Most math books, the letter name of the matrices has a mark over the top of it, like I said, and the square matrix has the 2 diagonals, a major and a minor. Only in the square matrices that has the diagonals that are perfect. Now, so here's some more examples. You had a single column matrix, which is also known as a vector. So it's written in the column format. So there's 3 rows, 1 column. You have a row matrix where you have 1 row, 2 columns, and then you have the square where it's 2 by 2s. Okay. Now, when we're talking about scalars, a scalar is just a multiplication. It could be pi. It could be the any type of constant, like the speed of light or something like that. That would be a scalar product. So when you're talking about scalars, you're talking about something you're multiplying it to. It's almost like a conversion factor in some senses. If we want to change from inches to feet, we know that we have to divide by 12. 1 over 12 would be my scalar at that point. So in this one, C matrix is a scalar times a matrices. So we would say the matrix C, the constant scalar A, is multiplied by a matrix D. Now sometimes you just call it, or you can see with the bars over the top of it. So multiplying each term by the number value, or the scalar, is the constant. So 3 is my scalar here, a matrix of A. So let's say it's a vector matrix and I have 3, 7, and negative 3. So all you're doing is multiplying the 3 by 3 gives me 9, 3 by 7 gives me 21, 3 by negative 3 gives me negative 9. Also, if a matrix has a common factor, it could actually be factored out and it will become a scalar. For example, I've got 15, negative 9, and 12. Those are all multiples of a 3, so I could take the 3 out and put the 3 in front of it. So it would be 3 and then the matrices, okay? So this would be a scalar multiplier. So matrix addition and subtraction. When you're having those to add or subtract the matrix, they have to have the same dimensions. 1 by 1, 2 by 2, 3 by 3, 3 by whatever. Both of the matrices have to be the same in rows and columns. So these two have 1 row, 3 column, or I'm sorry, 3 rows, 1 column. So you're just adding straight across. 9 plus 3 is 12, 21 plus 7 is 28, negative 9 plus negative 3 is negative 12. Okay? If I subtract the two matrices, 9 minus 3 gives me 6, 21 minus 7 gives me 14, negative 9 minus a minus 3 gives me my negative 6, because the two negatives make it a positive 3. Okay? When we're doing multiplication, it's a little bit different. There has to be a special situation set up. To multiply two matrices, the number of rows in one of the first matrix must be equal to the number of columns in one has to be the same as equal the number of rows in the second one of the second matrix. So in the first matrix, M1 by N1. In the second matrix, it'd be M2 by N2. So what it means is the N1 and the M2 has to be the same value, 3, 2, 9, whatever. If it's not, they cannot be multiplied together. Now, the product, the result when you're multiplying them together is actually the outside. It'll be an M1 by an N2. And I think this graph shows it a little bit better. This is how I write it to make sure that they work. So I write the columns or the rows and the columns down and the rows and the columns down. So then I make sure these two values, if it's a 3 by 2 and a 2 by 3, these columns have to be the same, or those rows and columns have to be the same dimension. Okay? Now, so if I'm looking at this, if it's a 4 by 3 and a 3 by 2, when I look at this, yes, these two can be multiplied because these two values are the same. Okay? Now, the resulting will be a 4 by 2 matrix. Okay? So again, if I have a 2 by 4 and a 3 by 3, if I look at these two values, then no, they can't and they cannot be multiplied together. Okay? So we'll do an example. I have 3 rows, 3 columns, and I have 3 rows, 1 column. So when I look at this, the N1 and the M, the number of rows to the number of columns is the same, and the resulting will be the number of rows and the number of columns. Okay? So let's do the example here, and I show it bit by bit. So what you're going to do is you're going to take, and I set it up this way just as a graphic. It makes it easier to see. We don't usually do matrix calculations by hand. We usually use our calculator or we use Excel. So we'll show you Excel how to do this later on. So what it's actually doing is you're going to take this first value and you're going to multiply 3 times 3 plus 3 times 5, 7 times 5, and negative 3 times negative 3 times 6. That'll be your first row. So this gets multiplied across. And then the second thing you do is you're going to do to the second column, but you're going to use the same values. 3 times 4, 7 times negative 3, negative 3 times 2. And they're all added across, okay? And you go and you do it again, okay? So when you, in the end, I'm going to switch back. In the end, your end result is going to be 26, negative 15, and 33. So it gives you a product of a 3 by 1. 3 rows, 1 column. Okay? Now, like I said before, if they don't have the correct number of rows and columns that you first looked at, then you can't multiply them across. Now, the next thing I'm going to do is we'll go over determinants, and I'm going to pause here and then we'll go over that.